the sixth in the series of the IIA SCOPE. Am I live? Great. Welcome everybody to the sixth in the IIA SCOPE Seminar Series. We're very happy to have Dr. Shylaja here to give this talk. She gave the first talk in this series, so very happy to have you back with yet another new work from you. This is, I think everybody knows Shylaja in Bangalore, but maybe some students might not. She did a PhD here under Vainu many years ago on ultra stars and binary systems. And then after a few years, she joined the Jawaharlal Nehru Planetarium in Bangalore as an educator, and then she retired a few years ago as the director. Her original research was on ultra stars, cataclysmic binaries, chemically peculiar stars, and so on, and molecules and comets. But then, as an educator, I think her field encompassed all of astronomy at some point. Of course, she's very well known both as an astronomy educator and a popularizer, as well as somebody who's done a lot of research in the history of astronomy, both in India and elsewhere. For example, a few of her works were a compendium of stone inscriptions in Kannada across the southern India, which have astronomical references dating back to 9th century CE, with Geeta Kaidala, astronomical alignments, and she has published papers on astronomical alignments in various temples and other monuments in southern India. She's done a lot of work unearthing writings of Raghunathachari from the Madras Observatory days and translating and publishing them, especially during transit of Venus. She's worked on a lot of Sanskrit and ancient texts on astronomy, for example, and mathematics. For example, the recent book on Ganita Kannadi, which you gave a talk on here before, as well as medieval astronomy, navigation, and so on and so forth. Every time I introduce her, I had to add one more book to the introduction because that's how she works. So recently, she edited and brought out a really big encyclopedia of all of astronomy in Kannada. It's called Khagola Darshana. It's in the library, so if you read Kannada, please go take a look at it. It's amazing work, and I think that will prove to be the reference for many years to come for everybody working in astronomy in Kannada. She's published six books in English and 15 plus now 16 books in Kannada. She's written more than 100 popular articles in English and more than 400 in Kannada in newspapers and newsletters and so on. Here she's going to talk about Laghu Manasa Vyakhya, a recent work done by her in collaboration with Puneet, who's sitting here. This is a new work, and it's part of a new project called the History of Astronomy in the Mysuru region, mainly in the Kannada language, which is being done under the aegis of the COSMOS Mysuru Planetarium project. And I think this is one of the first major works to come out of it. But I should tell you that they're working on 40 manuscripts from the Oriental Research Library, so there'll be 39 more talks in the coming years. So this is also the first seminar being given here in India, arising from the COSMOS project. That's also very good. So I invite Dr. Shylaja to come and tell us about this 17th century manuscript, talking about a 9th century manuscript, if I'm not mistaken. Yeah.
Thank you for that lengthy introduction. And I should have added Puneet's name here. Puneet is the one who brought the manuscript to a readable level, and I'm going to show how the manuscript looked and his efforts in bringing it here. I'm sorry that I did not add his name. Anyway, please, we'll remember because he is sitting right here. And this initiative by COSMOS is very good, as I'm going to tell at the end also. And out of the 40 odd manuscripts, I'm assuring you that there will not be 39 more talks, because not all of them are worth giving a talk here. And we selected this one for a specific reason, because this has some unique features in it. Okay. So Laghu Manasa is a work written by Manjulacharya. Some people call it as Munjalacharya also. It has computations on astronomical events like eclipses, conjunctions, heliacal rising and setting of planets, and so on. And this is the first book which has a reference for precision corrections, and he has actually measured and evaluated that and declared the numbers as 6 degrees 50 minutes between 522 and 932 CE. And he gives a very unique method of deriving the sine function, which is not found in the later books, because Bhaskaracharya and others, they give a different kind of a computation. This book was quite popular all over India, as we know from the commentaries. From Kashmir in 958 CE, just after about 100 years of the composition of this book. And there is a place called Prakashapattanam, which is very close to Patna. There also we have found a commentary. And in Andhra, this has a Telugu commentary, Yellaya. This manuscript also is available in Mysore, ORI. This Telugu commentary on Laghu Manasa by Yellaya. And there is one more in Telugu by Tammayajwa, and one in from Gangai Konda Cholapuram, which is near Chidambaram. So this was popular all over India, that's what I'm trying to say. And there are 7 or 8 more, all of which have been studied by Shukla in his monumental paper published in 1990. And the present text that we are discussing is from an unknown author. The name of the author is not written anywhere in the text. He refers to himself as a person from Karnataka Desha and gives the latitude. So that is how we know it. And this work, as I mentioned, was done by Shukla. He brought to light the uniqueness of this particular manuscript of Laghu Manasa. And he used the manuscript from Mysore Archives, my Oriental Research Institute, and that was because of K.V. Sharma, who converted them into Devanagari script and allowed him to use. So that is about the thing. There are 5 manuscripts in Mysore, and we have selected one particular one, which is called B583. The first part explains the rationale, and that is the one that has been used extensively by Shukla for comparing it with the other commentaries. The second part has a solved example of the solar eclipse dated 16 February 1607, and the third part has an solved example of a lunar eclipse which is dated 20th January 1628. So we have verified all the steps, all the calculations step by step, and verified that the calculations give very dependable results. So in the studies of Shukla, they are not concentrated on these solved examples, but only on the commentary. So this is how the manuscript looks. This is the page 31. Up to page 30 is the first part. 31 onwards we have started, and now we will appreciate the efforts of Puneet, because this is the one he had to read. And it's very difficult to read, as you can make out. The handwriting is not all that great, and even you can't sometimes make out whether it is an alphabet or a numeral. Fortunately, in all these texts, they have a method of decoding the numerals with the Bhuta Sankhya system. For example, for 90, they will say Kha. The Kha is 0, Anka is 9. So because of that, we are able to understand the thing. And although we were not able to get complete sentences, we followed the numbers. And then, because the method was known to us, so we started following the numbers, and then we were able to verify all the steps of the calculations. And this is what he converted that into. He wrote that first in hand, and then keyed it in, and so I was able to work on this kind of a very polished manuscript, and all that credit goes to him. What is the procedure that is adopted in this particular manuscript? It follows Aryabhatiyam, because this is dated 8th century, 9th century. So first step is to get the mean coordinates for the beginning of the year. We have to remember that the year count is in 2 ways, either the Shalivahana Shaka system or the Samvatsara system. Both are practiced even today. And the beginning of the year is the Chaitra Yugadi. That is the first day after the new moon, after the vernal equinox. So that is the civil calendar. So all the coordinates are brought to that. Then the corrections are applied for this. When I say mean, it is assumed that it's a circular orbit. So they first calculate it for the circular orbit, and then correct it for the elliptical orbit, and then all these are for Ujjain. So they apply the necessary correction for the location of the observer. That means the longitude of the place and the latitude of the place are hidden in the calculations. Then they get the coordinates and the instantaneous speed. what is the speed of the planet? When I say planet, I mean the sun and the moon and the node. All the three are called planets. And then they calculate the position of the node, which is called as the Rahu. And through that, they get the declination of the moon, which is very important in finding out whether an eclipse is possible or not. And then they calculate the exact instant of the midpoint of the eclipse, and then the duration on either side of the midpoint, before the midpoint and after the midpoint, and then the exact instant of the onset of the eclipse and the ending of the eclipse, recalculate the whole thing. Recalculating the whole thing, when I say, they have to get the coordinates of the sun and the moon for those timings, which can vary by a few hours, and then recalculate the whole thing. So this kind of an iteration, which is called as the asakrit process, happens, and in this text they have done it twice. So I will show how the results change after this kind of an iteration. And then they calculate what is the amount of obscuration, what we call as the magnitude of the eclipse today, that is the thing they calculate. So how to get the coordinates? So here you have a method which is unique to this particular text. So here, as I said, the epoch is Shaka 1100 or 1780. So on that year, on the Chaitra day, what was the value that is known? And this is the date for today, which is given as Magha Bahula 30, which means the 30th day of the month of Magha. So in between this, how many days are there? That is what we have to calculate. And because the civil calendar is a lunisolar calendar, there are many corrections that have to be added in terms of Adhika Masa and Kshaya Tithi. Some Tithis are generally missing in a month. So all those corrections, they have a calculation for that, and so all that you have to do. The rule that is followed is for 100 years. For 100 years, there are 36,525 solar days, which is equal to 357 lunar days, plus 36 months, plus. So this is the one that takes care of all the corrections that are needed. And this is the formula that gets converted into a formula like this for calculating a quantity called Dugana, which we will be using for all computations, because the interval between these two is 428 years. And what Manjulacharya, when he defined this, said was that this, whatever formula he is giving, is applicable only for 100 years. But now we are extending it to 428 years, and the commentators in between have added the necessary corrections for it. All those corrections are incorporated into this. So Y is the number of years, S1 is the Sankranti Tithi, that's the, I have written Mesha Sankranti, but the word Mesha he has not used. It's just the Sankranti, that is when the sun is on the vernal equinox point. What is this? This can be 6 days, this can be 10 days, so that number is needed. Similarly, another, this is the Chaitradi of this particular year, and what is this interval, that number also is needed. So all those things are incorporated into this. And this is how the reads. Dhruvabhya Abdagano, dig. Dig is, there are 10 directions, 10 multiplied by 10, that is, he is giving this. And then Swakiya, that means divide that itself by 8 and add the Sankranti Tithi, and then take out 1/60th of this, and the remainder of this should go here. So he says you compute this, put this in one place, and then after computing this, the remainder you add from the thing which you had kept in the first place, and then add the C1, which is the number of tithis from here to here, 330. They are not 330 days, they are 330 tithis. One tithi is the time interval taken by the moon to traverse 12 degrees. So that is how the civil calendar works. So this is taken care of here, and other number of seasons elapsed. All these corrections are added. And then we have 2 examples and the D values. Now you are working only with the 4-digit numbers. A similar calculations by later commentators like Bhaskaracharya or Ganesha Daivagna, or anybody for that matter later, even Ganita Gannadi, they will use 6-digit numbers, 7-digit numbers, because they also have the epoch as 1105. And the number for 428 years, you have to multiply it by 365. So that many number of days, so you are working with very large numerals. Whereas here, it is just 4-digit numbers, in spite of that being 428 years. Okay, so this is the advantage of this method. Now, what is the meaning of mean value? So, the motion of this is the example I have given for the sun. So, Aries, Taurus, etc. So, we compute how much did the sun move during these 428 years plus 330 days, and that comes to this blue arrow here, somewhere here. It is 10 Rashi. Rashi is a unit of 30 degrees. 30 degrees, that is 330 degrees plus 23 degrees, 33 minutes, 47 seconds. So that is the place you give. And then you have the Purva Dhruva, that is what was the value at the epoch that you have to add. So you get this, that was the number that is declared. And then you get the mean value, assuming that it goes by the circular orbit. So you have fixed the mean value of the position of the sun. Now you have to correct this for the elliptical orbit, for the longitude of the place, the latitude of the place, and so on. So how is that done? I will not give all those mathematical details, but I will just explain it. So whatever I explained with the help of the figure, he is written like this. So this is just these two lines will transform into a formula like this. Okay, so set down D in two places. It says Vida Samsthapya, put them in two places. In a lower place, add 10 times the number of years and to itself elapsed and divide by 70. Deduct the quotient from D out in another place and further subtract 8 times the number of years. So here it is. And then the next stanza says for the minute of hour. And then this is the Purva Dhruva, the epoch value. We add this. This is from the rule of Aryabhata. The Aryabhata says that this is the number of years in a yuga, and these are the number of revolutions. So I can't even read such a big digit here. And this ratio is converted into this smaller manageable ratio, and this is the one that is converted into the formula like this. So this is the ingenuity of Manjulacharya. So he has used the method of Aryabhata and then converted that into something that is easily manageable, because this kind of a calculation they have to be doing almost 5 or 6 times in a year. So managing with small numbers is very easy. No calculators, and no calculations. Okay. So now with the help of this, now there is a similar formula for the moon also. This is the rule of Aryabhata, which has been converted into a formula like this. This is the Purva Dhruva. And then they define what is called the apogee. This is needed for the correction for the elliptical orbit. The apogee also is moving slowly, and that motion is also available here. And so with the result of this, the position of the sun and the moon, this is the apogee, this is Rahu, this is the ascending node. Because there is a similar formula for Rahu also. But as you can see, we are not working with Rahu, but we are working with the one which is 180 degrees diagonally opposite to it, which is Ketu. So as you can see, it is between sun and moon, so there is every possibility of eclipse.
So the innovation by Manjulacharya is the series expansion.
No, there is no series expansion.
And this expansion, right?
No, deriving that manageable formula. He has not expanded anything. He has reworked the same digits so that it becomes a simple formula for you to operate. So you can memorize the two verses and then do this calculation.
So in the previous line, you had day 30. But all these Hindu calendars have only 28 days. Is this 30 coming after the corrections of Adhika Masa and all?
No, it varies. In 1 month it can be 29, the other month can be 30. So Tithi is 12 degrees. So the civil calendar will have a month for the 360 degrees movement of the moon, which need not be 30 days because it's not tied up with the movement of the sun.
Yeah, but always this cardia to this one, so this only 14, right?
Not necessary.
They add if you add that
No.
it
No,
will repeat also.
even after that, it need not be 14 days. Sometimes it is 15 days.
They add the,
Because
it will be repeated.
so the movement of the moon will be decided by its position in the elliptical orbit. So it sometimes moves faster, it sometimes moves slower. So if it coincides with the Amavasya, it will be moving faster. So in the 14th day itself, you will have the next Tithi coming. But if it is near the apogee, it will be moving slower. That correction, wonderfully it is incorporated into this. I will show you how. Okay. So now what I was telling was that this is the Ketu, the other node, descending node, which is between the sun and the moon. And so there is a possibility of eclipse. So whether it is feasible or not, how do they find out? That we will see. So this is the apogee, and for correcting it for the elliptical orbit, we need how far it is from the apogee. Because you know in an ellipse, it is the apogee that matters. And so we find out this is the apogee, this is the moon. So we take into account this angle, how far away it is from this. That is called as the Mandakendra. So that is the M. We have to take the sign of that, R sign, that is this trigonometric ratio, that is proportional to, the correction is proportional to that. I'll just explain how that happens in a simple way. So now let us say this is the position of these are the position, this is the mean circular orbit that we have, and this is the direction of the apogee. Depending on where it is, this is the angle Mandakendra, suppose it is here, this is the angle. So the correction you have to apply is proportional to the sine value of this and the size of this circle, this epicycle. This circle will be different for the sun, different for the moon, different for the different planets, and that is pre-decided. And so the ratio of this to this, because it has to complete one cycle in this, by the time it completes one cycle in this. So that is the idea that has been incorporated, and the sign of this is taken. And then you get the true, this is called the Madhya, mean position, and this is called the true position. So when you apply this correction for all these points here, you get an elliptical orbit. So that's the elliptical orbit. So you can see that when it is here at the perigee point, it is nearer to the earth and its movement is faster, and at this point it is slower. That idea is incorporated into the instantaneous speeds also, and here this is a sign correction that we are applying, so they apply the cos correction. The cosine of the same angle m is used for correcting the speed. So that goes by what we studied today as d by dx of sin x is equal to cos x. So it resembles something similar to that, although that kind of a rule is not explicitly mentioned anywhere in the text. It just says this is the gati, and so you divide it by cos. The same thing they do for the angular sizes also, which I will show later. The latitude, local latitude is decided by a very simple method. That is, you put a 12-inch pneumo. This is a standard thing. 12 inch is a common thing all over India, maybe outside India also. And this is the shadow length on the vernal equinox day. So that gives you the latitude of the place, and so that is called as Palabha, which is 12 tan phi. And there is a unit called Palakarna, which is also derived the length of this hypotenuse. This is called Palakarna. And that number also will be used elsewhere in the formula, because they take similar triangles and then apply this kind of a thing. So this is for the latitude. So you know the phi, and so you apply the corrections necessary for the latitude of the place. So this is a very interesting thing I was mentioning, finding the sine ratio of the angles. So they divide it into 3 parts, 30 degrees, 60 degrees and 90 degrees. So they call it the first sign, second sign and third sign. Sign when they say Rashi, first Rashi, third, second Rashi and so on. And these are the values. This is a number because as I mentioned, they don't take the when I say sine, we are taught that it is a ratio of two linear parameters, opposite side by hypotenuse. Whereas here it is the arc. So if I am telling that this is the angle, when I say r sine, I am referring to this arc length, which will be in degrees. So in this case, this maximum value has been taken as 8 degrees 8 minutes for some convenience. Now this is how he arrived at this particular number, etc. is all very intriguing, but this gives you a very interesting result. Now the text that we studied has not made use of this table, but has made use of this table, which was incorporated some 200 years later by another commentator called Mallikarjuna Suri. So here, instead of giving these, see, he has used the same numbers, but then for the third sign, he takes half the sum, half the difference, and so on. And this looks very puzzling, why all these things will have to be done. But then this whole thing is contained in a small verse, so you can memorize it. Otherwise also you can remember third sign 1, second sign 3, and so on. So for example, how to find the R sign of 1 Rashi 29 degree 53 minutes. 1 Rashi is 30 degrees. So it is effectively R sign 59 degree 53 minutes. How to find this? So for the first Rashi, the number is available 4. So you don't have to worry about it.
What is the original text for these tables?
It is given in the form of a verse.
Which book? Which text?
I mentioned about 3 parts of the manuscript. The first part contains this. First part. I am only concentrating on the second and the third one, which give solved examples. The first one gives the rationale. The book is available. IJHS published in 1990, volume 25. That has this paper. 200 pages paper is there, so you can read of that. Okay, and the book is with you. Okay, so this is in the form of a table.
Is it in English or Kannada?
Sanskrit.
Sanskrit.
No, but the
This is the
translation is there. Shukla is written in English. Okay, fortunately. So he has explained both methods. So how to use this and how to use this. This gives a better accuracy, as you can see here. So now the interesting thing is how he arrived at this. Nobody knows. But then the method gives you the correct result. So for first Rashi, you don't have to worry. For the second one, the second sign, you have to take 29.3. So he says the true multiplier is this 3 degrees 30 minutes that you take, and simply take this number in degrees as minutes and subtract it. Okay. Now don't ask me the logic behind this because he himself doesn't know. Shukla also was not able to
What
explain.
exactly is R sign?
Huh?
Lost track of R. What is R sign?
R sign is the way the sign ratios are expressed.
Okay.
Okay, so as I said, it is a arc. It is not a linear. It's not a number.
Okay.
R corresponds to the value of that radius. So in this book, it is 8 degree 8 minutes. So as I mentioned here, when I say R sign, sin theta is if you drop a perpendicular from here and take the ratio. Now you don't need to do that. You take R sign, that is R is the radius of this circle, and sin theta multiplied by sin theta, that will be the measure of this arc. That is R sin theta. In Karana Kutuhala and later text, they have used the number 120. Okay, but here he uses 8 degree 8 minutes. So what he has done is 3 degree 30 minutes, that comes from here, and he takes this 29, and this he calls as the multiplier, Gunaka. And this he multiplies by this 29.53. 29.53 into 3 degree 1 minutes and divided by 30, you get some number. Okay, and the text specifies that we multiply this by 2 and divide by 60, which is essentially the same thing, because this has some other advantage of directly you will be able to convert it into arc minutes and arc seconds. So that's the advantage.
So in the original text, these numbers are by words.
Yes.
Okay.
They give the number as Bhuta Sankhya. That means it will not be numerals written down, but some words will be written down. Okay. And then you take this 4 here, and this number you add in the degrees place. You take the same number here, you add the same numbers in the minutes place, so you get something. And so finally the value you get is, the R sign of this is 7 degrees, 7 minutes, 18 seconds. You can verify that with the calculator. You can take what is the value of sine of 59 degree 53 minutes and multiply it by 8 degree 8 minutes. Now, you see here the type of multiplication. You have to multiply 29 minutes 53 seconds by 3 degree 1 minute. No, it's not easy. So he gives a method. We are all used to decimals. So if you are asked to do that, you will convert it into a decimal and then use the calculator. But they were doing it in a different way. So that is some kind of a multiplication which perhaps our grandfathers did for rupai anekas. When they had to multiply, they used to do that. Or feet, inches, and so on, for that kind of a thing. So you multiply 29 by 3, 29 by 1. Put it in a proper way and multiply 53 by 3, 53 by 1. Put it in a specific way, add all of them, and then transfer them according to the ratio of the numerals. And so you get the value. Now, all these things you have to do with hand. So this kind of a multiplication he calls as Chatushpratinyaya. That's the word that is used. I didn't know this for a long time. When I was studying this, I came to know that that's the same thing. And very interestingly, this has been referred to in later texts also. But yes?
One question. When we are reading normal Sanskrit slokas, then how do we know that it is a Bhuta Sankhya or a normal one?
Oh, you can make out. I showed you an example in the previous one.
Okay.
It says Dashagna, that is easy. And simply it says Kakhangaihi Hatva. So you know Kakhangai. Yes. I mean, it's a standard thing in all these kinds of text, you come across that. And in the later text, I was referring to this Chatushpratinyaya. For example, the one Brahmatulya Udaharanam, which I work with Shubha for this, they call it Gomutrika. You understand what is Gomutrika? I don't know why that name has come here. Maybe because when the cow is walking and urinating, it goes in a zigzag way like this. I don't know. Okay, so that is the word that has been used. Anyway, this is a very interesting way of finding the sine ratio of any angle, and this has been used extensively in this text at least 7 or 8 times. Because we have to, how do you find the cos? They say that you take 90 degrees minus of that angle and use the same table. So they don't give the cos separate table. Okay.
So
then
we have, I mean, was he saying you have to actually, Chatush something you said, no, the work out. But no text gives the working out, right?
No.
None of the manuscripts
No, this shows.
Shows the
This shows.
work out.
It says you do Chatushpratinyaya, you get this. So I worked it out actually.
They actually number writing and solving it. Does it appear in any of the manuscripts?
No. This one gives the numbers. So I have worked it out. I worked back and said how did
previously
No. That's the advantage. That's why we chose this particular text, because this gives the solved examples. Otherwise, if they simply give this Sparshakala and Mokshakala, then how did they arrive at that? We will not know. All these steps, individual steps are given in the text.
Solid example would be in form of shloka only, or? That solid example would be in form of shloka.
No, they give just something, they don't solve it.
Shloka will be given. Below that, there is a running text, commentary. That will also have the numbers. Okay. So,
it's like notes.
Yes.
Like
yes.
when some
Exactly.
teachers we write ourselves.
Exactly.
Yeah, but it doesn't solve it.
That's a master copy. You can have it. First one.
They won't solve it like the way you do it.
No, not at all.
Like do this, like in words they may write, like if you do this, write that.
No. If it was so simple, I would not have spent so many months on it. No.
I mean in code words which you would have.
I will show you how I calculated it.
Yeah, that
for one small thing, I think I spent a page full.
Okay, that would be great to know. How did you decode?
Let us come to the finding the longitude of the place, because the correction has been indicated as 16 arc seconds. So we have to use this this idea that the difference is 16 arc seconds. So he says this is because we know how far away from the meridian it is. And how do we define the meridian? The meridian is defined in all the text almost, but the names of the towns they use are different. So here he says that it is passing through Kanchi and then Ujjain. Okay, there are some places in between. So this dash line is the meridian he is referring to. We were working on yet another manuscript which Shubha is still working on. There it said Kanyakumari and Karnataka Desha. So Karnataka Desha can be this whole thing. So how do I fix the meridian? Similarly, perhaps Kanchi was not just one town there, but maybe the entire region. I do not know. So we were working with a manuscript which is from Mahad in Maharashtra. So there it was easy because either way, whether I use this meridian or this meridian, the correction there of this is the distance in yojanas, 30 yojanas, works out. But we could not do that here. Because if I take this number, it turns out to be some 15 or 20 yojana east of the meridian, which takes it into the ocean. So I was really puzzled, so I have gone as far as possible. There is no town there. The latitude is easy. Latitude is easy because the Palaba is given as 3 degree 10 minutes. So I could calculate the latitude as 14 degrees 15 minutes very precisely. Whereas the longitude, I have a problem. So here, there is a little town called Gudur. So I thought maybe he was living there. So I do not know. And it is in Kannada. So maybe Kannada was being used all over here, or Telugu, Kannada had the same script, I do not know. But in any case, the place is somewhere here. So it is some Gudur in Andhra Pradesh. So that's where he worked. And all the verification I have done for that latitude and longitude. So after all these corrections, we get the spashta, that is the true value. So these are now corrected for longitude, latitude, and elliptical orbit. So here, these black things, these are the original mean values here and here. So the revised ones are S dash, K is K2 and M dash. They are so close by, so there is every possibility that there can be an eclipse. And the value of these two are same. 10 Rashi, 19 degrees, 52 minutes and 40. These are called Samakala Ravi Chandra. That means only in this last thing there can be some small difference, but otherwise to the accuracy of minutes it's the same. And the revised value of K2 is this. So the difference between K2 and this is only 5 degrees. So the node is just 5 degrees away, so you have a possibility of eclipse. And this is the value for Rahu. Now they calculate the diameter. Again it follows from Aryabhatiyam. These numbers are in error. These numbers are in error, but doesn't matter, we are taking the ratio. So 7390 divided by 224. This is the number, mean diameter of the sun. And for this they apply a correction which is 8.8 r cos Mandaphala. Mandaphala is that correction which we had arrived at for the elliptical orbit correction. So that is applied here. And for the moon also a similar ratio, and for 97 they apply this correction. So when it is near apogee, you have a larger size of the disk, and when it is near perigee, you have a smaller size of the disk. So the bimba is also corrected for the respective distance. Now we have to get the latitude of the moon, how far to the north it is. So because that again decides the thing. So we all know that the moon's orbit is slightly tilted from that of the sun. Here. So this is called as Vikshepa. This is the latitude. So again you take the sign. This 270 minutes is the 5 degree tilt. And so this is called the Vikshepa. So now this is the disk of the sun at the conjunction. This is the disk of the moon. and therefore this obscuration is FC. This portion is covered by the moon. How do you get that? That is decided by the separation between A and B, which is the related to the Vikshepa. So there is a formula again, it's very simple one, you can derive this itself. And AC plus BD is called as Mane Yogadha, means half the sum of the Bimba. Bimba is the diameter, half the sum of the diameter is the sum of the radii, and that Vikshepa is the latitude. If you remove that, you will get whether, suppose it is more than that, then there is no eclipse. So this is the way the possibility of eclipse is decided. And then now comes the finding the time, duration of the eclipse. So when it is first contact, you know that they are just touching. This is the moon, this is the sun, they are just touching. So the separation between them is the Mana Yogartha again, the sum of the radii, and this is the Vikshepa. So you need BC, and BC is now in this triangle you are getting in terms of angles, convert that into time units. So that is how it is done. The first contact, separation between the sun and moon is AC, which is the sum of the radii. The moon is not on the ecliptic, but it has a latitude to the north, so it is Vikshepa. So BC provides this, so you get the simple, it is called Bhuja Koti Nyaya, Pythagoras theorem. The opposite side is called Bhuja, the adjacent side is called Koti, so this is Bhuja Koti Nyaya, and using that you get the time. Okay, so these are the angles, and that is the difference in angle. Convert that into time units, you get 2 Gati, 10 Vigati. This is hour minute, something equivalent of that. That is the duration of the half eclipse. It is called Sthityartha. So this is how the time is calculated. And then you have to correct it for the location of the observer. That means you have the sun not on the meridian, but it can be elsewhere. So the correction is decided by that angle, which we call as the hour angle, on the east-west side and the north-south side, both. So it depends on the location of the observer. So for that you have to calculate the hour angle. Calculating the hour angle is not that easy. So what they do is, you know the position of the sun on the ecliptic. The blue line is the ecliptic. But what you want is on this circle, diagonal circle, which is marked in red. So you want this as the hour angle. So for that they calculate what is the Lagna. Lagna is this one. And before that you have to apply the precision correction so that you can get the declination correctly. Otherwise the declination part will be large. So effectively projecting this blue line onto the red line. And for that they calculate what is XL, the Lagna, and based on that they calculate what is XA, and based on that they calculate what is BA. This is the difference in the on the meridian, and that they apply here, and then they get the XF part, and so what is BX part. Tedious calculation they do by iteration, and finally they get this, and the correction for parallax is called Lambana, which is h into h minus 20 divided by Palakarna. Palakarna is that hypotenuse which I mentioned earlier. H is the hour angle. So this rationale is, if you are, this is the earth now, you are standing here at this position O, and if the conjunction occurs right here on your zenith, no problem, but it doesn't happen. You can be at the horizon also. So when you are here, the conjunction is happening when at the maximum angle, which is about 100 arc minutes. So this formula has been coined so that you get a maximum value of 100 arc minutes. This is an empirical formula. So there is yet another empirical formula like this, which gives a very, very dependable result. So this is the kind of correction that has been added for getting the precise value of the instant. This correction is added to the timings that we calculated earlier. So the details of the calculations are here. So you have, this is the first contact, this is the last contact, Sparsha and Moksha. Sai and Ravi is the value of the longitude of sun corrected for precision. Otherwise, it is Nirayana Ravi. What we calculated earlier was all Nirayana, no precision correction was added. And then they calculate the Sayana Lagna, then Grahona Lagna, the difference, and then this Lambadyugata, and then this Nata, this one, and then you get a multiplier, and using this, you find out what is the correction. So the revised Sparshakala and Mokshakala are all calculated, and Adyanta Punyakala is the duration of the eclipse, which is 4:30 and 11 minutes. So this is how the calculation is done. Once you get this, insert these numbers and redo all the calculation for a second iteration. I show only the results here. So this is the meaning of Sparsha, the first contact. This is the Madhya, the midpoint. This is the Moksha. So the timings are 17, 30, 31 Vighati for Sparsha and Moksha. And if you apply the Lambana correction, it becomes 20, 50 and 25, 16. After second iteration, you see the numbers slightly change. We convert it into hours and minutes. And then convert it into IST by adding the sunrise time for this location, Gudur. And then the actual time works out to be 1508 and 1648. And this is the XGBR application I used for getting the timings. And I placed the cursor here and got it. So you see that the difference is just 2 minutes. To that accuracy it works. Okay, so this method works very well. Now we have the example of the lunar eclipse. So lunar eclipse also the same method. I will not repeat all this. Same Dvigana and mean values, all those things are calculated. Rahu, Ketu, etc. So these are the mean values here. And these are the true values, that is corrected for eclipse, for the elliptical orbit, for the longitude, for the latitude, everything. Now you see that Rahu is so close here, Rahu is so close here, the two are exactly 180 degrees away, so there is every possibility of the eclipse. We calculate the possibility of the eclipse in the same way, but this time the objects are the shadow and the moon. Okay, so how do we get the shadow? How do we get the shadow diameter? So this is a very, place the water from there.
Oh, is that?
Okay, thanks. So this is a very simple way of getting the shadow diameter. These two similar triangles, this one E dash, S double dash and this. This is the sun. This is the radius of the sun. This is the earth, the radius of the earth. This is the shadow radius. The shadow radius, that is mm dash, is at the distance of the moon. So this is a very simple formula, and you get a fraction here, 7. You insert all the numbers here from Aryabhatiya. You get this number, and this 97 again they correct it for the elliptical orbit, because both the orbits of the sun and the moon are elliptical. Once that is done, you calculate the duration of the eclipse in the same way, but now it is the shadow. This is the shadow and this is the moon. So this is your Mane Mugharda, sum of the diameters, and this is the one that should be converted into the time units. So this is done. So you have here diameter of moon is 33 arc minutes, and the diameter of Bhuchaya is 94, and so on. So you get the timings. So what is called as sthiti is there, that is partial eclipse, duration of partial eclipse. So this is the first contact, this is the last contact, Sparsha and Moksha. And they vimarda, that is totality, is generally possible in a lunar eclipse. This is called Unmilana and this is called Nimilana. So the duration between this is the duration of the total eclipse. So we calculate the duration in the same way as we did for the partial eclipse. And Mana Yogartha minus Chandra Bimba and so on, the same Pythagoras theorem, etc., etc. So we get the duration of, semi-duration of the total eclipse as 1 Ghati and 53 Vighati. So these are the results. So you have here first contact in Ghati units, and Unmilana midpoint, Nimilana third contact, and Moksha last contact. And these are the time intervals. They have to now take from sunset, not sunrise, but sunset instant. And when we do that, we get IST as 2509, which means it goes to the next dawn, 109, 214, etc. And again from Xavier Dubier, we get the timings. So what you can see is that it agrees so well. Here, this is calculated is 109, this is also 109, and this is 214, this is 208, this is 300. So there is difference of just a few minutes here. To that accuracy, it works. So this is the way the results have been computed, and the method is applicable even today. So what are the unique features of this text? It's introduction of the Dyugana, which is just a 4-digit number, which makes the whole calculation so simple. So that is the important thing. Then the instantaneous velocities, they have already started using the cosine function. So whether it has an extrapolation of the differentiation part, we do not know. And the elliptical orbit concept has gone into not only getting the spashta, the true values, but also for getting the diameters and the instantaneous speeds. The precision correction, he calculates it to the date, not just that year. In the other text, they just give it for the year. But in this case, for the given day, also it is calculated. And the interpolation of the sine ratio for a given angle is very easy to use. And there are two empirical formulas that have been used here. The rationale is not known, but Shukla also remarks that it must be based on observations. So there are two examples, as I mentioned, that are spaced apart by 20 years. So the solar example has the Kannada script, but the phrases that are used, sometimes there are no sentences at all, just the phrases, they are all in Sanskrit, but the script is. The other one has some Telugu verbs in between. No, it is Kannada script. So for example, it says in the solar eclipse concept, it says Hatva, that means multiply. Here it says Guninchi, so that's the Telugu part. So this, to that extent, the Telugu words have come in there. And the handwriting looks very similar, but the last page is really messy thing. We just could not make out anything that was written. There were a lot of errors also, misprints. Misprints means some strike through and rewritten, all kinds of things are there. But we managed to get it because we had worked out all the things step by step. So we were even able to make out what's the mistake that has happened in that. So this is the last page. As you can see here, there is some strike through here, some gaps here. He wanted to write something there, but he forgot to write. And this Parvakala, Mokshakala, they are all interchanged. All kinds of things have happened here, and even handwriting is not that good as it was in the first page. So maybe he scribbled. And very interesting thing is this last line here. You see a date there, 9/11/88. Now this looks like 9/11/1898 or 9/11/1798. We do not know. And there is a thing, something which looks like a signature here. The color of this part is slightly different. So it is not very obvious here. the color of this page number also is different, the color of this also is different. So maybe this was added by the person who collected it later on. We do not know that. Huh? No, it is not Hale. You can manage. It's understandable. I mean, in 400 years, I don't think it is not all that different. And so this is what it is. And so these are the conclusions. So this is an example of the scholarship across different regions in India. Because the same book has been used extensively from different regions of the things. And we see that there is a continuous effort to improve. There is a very interesting way. You know, these Sanskrit verses are written in some chandas, some meters. The entire text is written in a meter called Arya. Whereas there are 3 verses which are right in the beginning, which are in another meter called Anushtu. That is done deliberately so that after 100 years, if a person wants to use the text, he has to bring in fresh value of constants and introduce some corrections. So he will know that this is the place where I have to incorporate this. So we see that from Prashastidhara to Mallikarjuna Suri there is a difference. From Mallikarjuna Suri to Ellaya there is a difference, and so on. So this kind of a correction, they have made a provision for that in the method of writing it itself, and they put in some annual corrections other than this called Bija. Bija is an annual correction which is perhaps based on the observation, although it is not mentioned. So year after year, so here the correction, Bija correction for the first eclipse is different, for the second eclipse is different. So that is something they keep on calculating and recalculating and providing in these kinds of manuals. And of course, expertise on the use of trigonometric functions in the 9th century itself. And solved examples, the emphasis is based on the method of iteration. So this is also easily verifiable. We have verified that, as I showed you in the case of the solar eclipse, 2 iterations have been done. In the case of 3 iterations. In the case of lunar eclipse, 2 iterations are done. So we need to search these kinds of examples in other languages, because all the while the concentration has been only on text written in Sanskrit. So now that we have found that these kinds of examples, we should look for such manuscripts in other languages. And that way the initiative by COSMOS, I am thankful to this, because we have been able to access these manuscripts which had been lying untouched for nearly 400 years, and we are now able to access them and then understand what is written in them. So thank you, and I think I have conveyed the uniqueness of this thing. Thank you.
Thanks a lot, Dr. Shylaja. I think that was a very interesting talk about something none of us have much clue about or much knowledge of. I think we've all been enlightened really well today. So before we start some questions of the audience here, request people on Zoom and YouTube to also type in your questions. People on Zoom can also raise your hand and I'll call on you. So first, let's take questions from, Amisha.
So you mentioned,
Please wait for the mic because it's also recorded on.
you mentioned the Pythagoras theorem had an Indian name. I don't remember that. But what was the first time that was this theorem was referred in the scripts that you have been studying?
700 BC.
700 BC. But that is
Name is not written.
Who actually
Shulba
gave this
Sutras.
name?
There are texts called Shulba Sutras. There they use it casually. They don't mention. They just mention that because this is the Karna, we get the side as this. Casually they mention. They don't give a name. This Bhujakoti, Karna Nyaya, etc. only in the recent 1 or 2 textbooks they mention it, but not always. Even in this text they have not used that word. They have not used it. It's as though you know it
You
anyway.
know it. They did not. But the first time it was occurred, that is later than later than in time compared to when actually it was found by Pythagoras or before.
Pythagoras.
Yeah, he was very long time ago, right? So how does it, like, there was no communication or anything. Like, can we claim it was first climbed in?
No, you please see the lecture by Rodham Narasimha. In that he mentioned that Pythagoras had nothing to do with the theorem.
Okay.
So it is somehow the name got attached.
Okay, but what I meant is in the European or the Western, they found something, but then maybe it was already there in.
Yes, it was there.
So, but the timeline we don't know, or like exactly
No,
we cannot
there are three Shulva Sutras. One is dated 700 BCE, the other one is 800 or something, the other one is much earlier. So in all the three you have examples of this. So the one which is exactly dated is what I mentioned as 700 BC. I may be wrong by plus or minus 100 years, but that's the order. Okay, much before Pythagoras it was known.
I think the Pythagoras triplets before Pythagoras was also known in Chinese manuscripts and Middle Eastern Babylonian manuscripts. I think many cultures seem to have known at least the triplets, some of the famous triplets at least, before Pythagoras. That is evidence.
Yeah, 5, 12, 13, all these things were known.
Yeah, but they didn't climb here in Eastern culture. Nobody
No, but
climbs. Or
nobody considered that it is something worth claiming. You know, 2 into 2 is to the 4. You can't claim that I was the first one to it was as casual.
Yeah, other comments and questions, please. Yeah.
So how does different authors writing the text in different chandas translate into improvement in the calculations?
Because they incorporate in those 4 verses the corrections that are necessary because you have made some approximation in the formula. Okay, now if you were to do that with the calculator, your calculator can take it to 8 decimal places. Whereas there, because it's a handwritten hand calculation, they would restrict it to the number of say arc seconds. So fraction of the arc second part is ignored. Well, that accumulates and over 500 years it will lead to an error. Now for that they will say add 1, because in all these cases they say that weekday is a running number. So Varasamya it says. That means if after all your calculations, today according to the calculation it should have been Thursday, but you know that today is Friday and therefore you add 1. 1 is the correction. So that kind of a correction you have to add. All these things will be written down.
Is it because of the way that we could write number of words in a shloka? So if we add up, it will become a different chandas.
Yeah, that is the meaning of chandas. Yes. But in that, the idea of introducing the entire text in 1 meter and only 3 or 4 in another is making a provision for introducing corrections. Okay, in the other text that I am studying, they have instead of writing 0, 2, 2, instead of writing 2, 2, they have added a na in the beginning and said 0, 2, 2. Nobody writes a digit as 0, 2, 2. Then he explains why I have added is this formula is valid for 100 years. After that, you will have to, it will become 1, 2, 2. Then you will need a place for that, so I made a provision for that. You know, this is the kind of trick they were doing.
The ancient Y2K problem was solved, basically. Other questions and comments? Rajguru.
The manuscript photo, the first page and the last page, you showed that's the original manuscript?
Yes, that's what he took from the Mysore Oriental Research Institute. He took copies of that and he has done handwritten.
So I'm just wondering, so it looks like written with the blue ink. 17th century, I'm just wondering,
it's a paper manuscript. It's a paper manuscript. It's possible that it was copied later on once the paper became available. Paper became available here maybe in the end of 18th century or so. Yeah. So somebody subsequently copied it. That's why I said that the date may be 70. It could be a British person also. Somebody locally copied it, and then the British person put the date on it. It's possible.
Okay.
Because they were going from village to village and collecting all the manuscripts, and they put all that in the Mysore library.
So how long did you take to verify? You said all these calculations you
About 6 months, right? He first gave me the handwritten version 6 months ago, and then we had to break our head because there were so many gaps. So I had to redo the calculation, redo them till I arrived at the numbers they had, because there were so many missing points there.
Yeah, I have a couple of simple questions. What's the word used for elliptical in
They don't use the word elliptical at all.
because it was like elliptical
No,
correction.
I showed you that because you will understand it, but they don't use it. They say that it is manda phala and manda correction. Manda means slow. It has nothing to do with elliptical. Where this is only for the sun and the moon. For the other 5 planets, there is another correction that you have to apply because they have a relative motion relative to the Earth and the sun, and that is called as the Shigra correction. Shigra means fast. Shigra has nothing to do with the speed here. So it is the correction for the relative motion there. It's the correction for the elliptical orbit here. I use the word elliptical orbit so that the idea hidden in that is obvious to you. That's all.
Another question is, can you, like, one nation is how much? What is the distance?
About 5 miles.
About 5 miles.
Some people quote 8 miles also. I use the word 5 miles from the text of Raghunatachari, which is here. Raghunatachari clearly gives, because he was aware of the mile units also. So he gives 1 yojana is equal to 5 miles.
So just to follow up, so the elliptical orbit, the observations which essentially related would be the size varying. Is that how they?
Timings of the eclipse.
No, I mean, if you follow the moon, the fact that they knew the
The
corrections.
2 things at the time and size.
So that must have been partly from size observations.
Yes.
Okay. Yeah, Anup.
Yeah, so there's 2 things. One is,
Mike.
there's a lot of glossary involved here. Like, what means what. So is there a dictionary where one can look at what this means what?
Oh, very interestingly, I found one. You know A.G. Kulkarni. A.G. Kulkarni just today sent me he was the director of the Baroda Planetarium, and he is from Osmania. He was here in IIA for a while. He just casually sent me a PDF today saying that it is some kind of a manual for all these technical terms in Sanskrit, and he asked whether this has been translated into Kannada or English. Unfortunately, it is not translated, so if somebody takes it up, it's a small book, it would be very interesting, because what's the word used for hour angle, what's the word used for horizon, for meridian. If somebody is able to transfer this now, because I know this audience, I have not used those technical words as far as possible.
Yeah,
But
what is
otherwise,
this book like, it is in Sanskrit,
Gola
right?
Paribhasha, it is called Gola Paribhasha.
Okay, Gola Paribhasha. So it's written in Sanskrit versus only Sanskrit words are collected.
Yes.
So, but that Sanskrit words have to be having a corresponding currently used word.
Yes.
So one has to match it.
Yes.
Okay.
No,
excellent.
it took years for me to understand that.
Yeah, of course. This is some
because there is no such book. You are right. There is
Yes.
no such book.
Because it is then one can.
I would
actually
look at
use
the
that.
diagram. I would the person who teaches that in the classical way. How does he do that? He has
so
memorized
that
it.
knowledge is actually lost.
Lost.
Right? Because
So
we
I
had
will
a
ask him
system
to. He will tell me in the verse form. I said, please put down in the diagram. Then I understood. Okay, he's talking about the hour angle.
So basically, we have lost the knowledge system of.
It also has created a gap
Yeah.
between the traditional scholars
Yes.
and the modern astronomers.
Maybe it's idea for next book of yours.
No, it's too much, because Gola Paribhasha is already available, and only somebody has to sit down and translate them into
The
English.
corresponding English thing.
Because if I do it in Kannada, it has no meaning, because in Kannada also, in Telugu also, the
There's
same
no
words are
local-
used. Same words are used.
Okay.
So only when you transfer it into modern spherical trigonometrical terms, which I used in this talk. Okay, so that
will actually open up someone to actually look
yes,
at and read
yes,
that.
yes.
Of course, you need to know the language also.
Yes, yes.
Right. And second question is that the corrections they I never come across any observation made by people how they observe. We only know about calculations and the end products are only your it's transferred to you.
Yes.
But what goes behind anywhere, anytime, nothing is there.
No, nothing is there because as I mentioned here in these two examples, they are spaced apart by 20 years. Let's say he wrote this book after the second eclipse. Then the bija correction, the annual correction he applied for the first one is different, for the second one is different, which we should assume that he got it based on the observations.
So how did they do the observations? What was the no log, nothing is...
The Parilekhana is there.
Okay.
What they say is that you make a drawing of this and compare it with what you see in the sky. Okay, that's all. It stops at that.
So you create your own charts. But there is some indication of charts prepared or something.
Yes.
Okay.
We are trying to prepare, even that is not easy. So many things are sort of taken for granted. You know this anyway. You know this anyway.
Maybe you also mentioned the work, I think you told me earlier about you and somebody recreating some of the astronomical instruments used in those days, right? Not just Shanku, but the water clock and all that.
Water clock, those things are there, but then how to check the accuracy? You don't know. The Ghatika we can make out. 24 minutes is equal to that. All that is possible.
Yeah, other questions? Yeah. So this is astronomy, archaeology, linguistics, history, all rolled into one project, right? It's pretty amazing. And geography.
This same thing can be used by people who are interested in the development of the language. Because how the sentences are written and the Kannada that we speak today is slightly different in terms of the words. So how did they evolve that? That is also possible.
Do we find examples of Bhuta Sankhya in Upanishads also?
Upanishads, no, I don't think so. There is...
For example, if one encounters any form of numerals in Upanishads, in words, should we interpret them as...
No, the only place where I can think of is that in one of the Upanishads, they say that the joy of the human is some 10 times that of somebody, Deva, and the joy of that is 10 times that of somebody else, and so on. There they use the word Dasha, Sahasra, and so on. So I don't think they use Bhuta Sankhya there. But Leelavati, for example, is full of Bhuta Sankhya.
In Mandukya Upanishad, I think there are like Saptanga, Ekona, Vimshati, Mukha, something like that.
They are numbers. They are not Bhuta Sankhya's. They are numbers. When I say Bhuta Sankhya, instead of writing 2, I will say a Netra.
Okay.
So that's the way. Okay, so if you use the word Netra sometimes in a shloka arbitrarily, where the eye has no meaning, then Netra means 2.
Amazing.
Can I take a few questions from Zoom and YouTube and come back to the audience? Right? Okay. So Amogosha wanted to talk. Amog, you just unmute yourself and ask.
He's asked. Yes, you are. I have to pull out my notebook. Okay, I'll show you. How will I show that? It's a notebook.
You can keep it here and people can see it when we leave. Okay, thanks. Yeah, thanks, Amog. You can see it when she comes to my side. No, I think. So, by the way, if you're coming to ASI, Puneet has a poster on this work at the ASI as well, so you can also take a look there.
So at least one page in the camera.
More than 2
The camera is there. It's on Zoom.
Okay. How do I show this?
Yogesh, I don't know how close it can focus.
You can just take a picture and send.
Yeah, we'll do it.
Yeah, I can show you here. See, for Rahu, it says that you add 449 years, Rashi, degree, minutes, seconds, 449, 9. Oh, I can write on the board.
Perfect.
So here it says 449 years and 9 Rashis, 10 degrees, 59 minutes and 16 seconds. Okay, this is some number. Now this number you have to divide by 20. You have to divide this by 20. You have to divide the same number by 265. This number, this is called some, yes, okay, it has a name. And then add it. Now, this is number of revolutions, this is Rashi, this is degree, this is minutes, this is seconds. How do you divide this?
So degrees will not go beyond 30, is it? The shall be less than 30. The degree will not go beyond 30, so it's within 30.
No, because this is Rashi.
No,
If it becomes more than 30.
Yeah, one Rashi is 30.
In fact, you can combine this and make it 9 is 280. Yes. So this is 280 degrees. Okay. So how do you divide this by 20? You divide 449 by 20. Take the remainder. Multiply it by 360, convert it into degrees, divide that by 20, multiply it by 60, make it minutes, and so on. I did all that. And finally, I got the value that he had. So I was, okay, what I have done is correct. This is one example. And for the sign also, for finding the sign also, you have to multiply. I have made mistakes and corrected it so often. So many times I have done this calculation.
So this is the 21st century manuscript commentary on the 17th century manuscript. So I think this we should make sure we scan and keep in good
Here,
control.
dividing it by 265 was really tough for me. So I had to.
Writing this as a book?
Huh?
You will be publishing a book on this?
I have not thought
Paper.
about it. It's for COSMOS to decide.
But you're publishing as a paper, right?
Huh?
You're publishing as a paper.
Yeah, I plan to publish a paper right now. But then all these kinds of details, I may not be able to do that. So first, for dividing it by 265, I divide it by 265, I get a quotient. I write it somewhere else. Then I get a remainder. Remainder I multiply by 12. And then I get the corresponding Rashi, I add 9 to it. Then divide that by 265. Then I get a quotient of 8 and so on. I have to do like this. So it was a very tedious.
So you were true to the actual method.
Yes, this was the way they were doing it.
So there's a question from YouTube from Kavin Kumar. What is the exact thought behind the motion of planets where they epicycles with different rates of motion, and that's why the corrections were needed? And was the mean planet a representation of a real planet, or what is a mean planet?
Mean planet is it is assuming a circular orbit. Where is the position? That is the meaning of mean planet. But because it is moving in an elliptical orbit, that will not suffice. So you will have to apply the corrections.
Other questions that come from yeah.
Are you told that cos function derives?
Yeah, Mike.
You told.
Yeah, hello ma'am.
Yes.
So you told there is a derivative in one shloka, it refers as like derivative of sine.
It did not say derivative, I said.
Okay.
He doesn't use that word.
Okay. Okay.
Now continue.
Like, is there something related
No.
So maybe you could
to
explain
cause?
a little bit more about that.
Now, for example, he says somewhere he wants Koti Jia. So what he does is that he takes the difference with 90 degrees and takes the sine of that. Okay, that is how cos is defined. And why did he want the cos? Because the instantaneous value is needed. Okay, I showed you the example of how the diameter is calculated and the divisor is corrected for the Koti. That's how it is. Koti means cos, bhuja, jya means sine. So whenever they use that word, that R, I mentioned in the beginning, 8 degree,
Koti
it
is
means.
a point or point. That is exactly the Pythagoras theorem. Also, Koti is coming because of
Yes, adjacent side and opposite side.
So they said that instantaneous rate of change for the sine values, you just do cos. That much they said.
That's all.
Thank you.
There's another follow-up question from YouTube. Is the mean planet something they had conceptualized since olden times, or something you have added as a representation to better understand it as an elliptical orbit for pedagogical purposes?
They use the word Madhya. Madhya means mean planet. So it's a very old concept. It's in Aryabhatiya also.
Okay.
Madhya and Spashta. These are the words that are used.
So, last comments, questions?
Okay.
If not, let's thank Dr. Shylaja again for
I
a
thank
wonderful
you all
talk. On a topic which I think is new to all of us. I think we learned a lot today. We also learned about the scale of this project and how much work lies ahead. So, we look forward to your future talks and papers as well. So thanks.
Thank you for all the patient hearing. Thank you.